1I ʻOumuamua. On October 19, 2017, the Pan-STARRS 1 telescope in Hawaii detected a faint streak of light moving rapidly across the constellation Lyra. Initially cataloged as asteroid A/2017 U1, this object would soon revolutionize our understanding of interstellar visitors and spark one of the most contentious debates in modern astronomy. The discovery itself was almost accidental. Pan-STARRS, which stands for Panoramic Survey Telescope and Rapid Response System, was designed to hunt for potentially hazardous asteroids that might threaten Earth. The automated system photographs the same patches of sky multiple times each night, looking for objects that move between exposures. When astronomer Robert Warwick examined the data, he noticed something unusual about this particular moving dot. Within days of the initial detection, follow-up observations revealed the object's most extraordinary characteristic. Its orbit was unmistakably hyperbolic. The orbital eccentricity measured approximately 1.2, meaning this visitor was traveling far too fast to be gravitationally bound to our Sunday. After careful analysis of its trajectory, astronomers confirmed they were witnessing humanity's first detected interstellar object. The International Astronomical Union faced an unprecedented naming challenge. No classification system existed for interstellar visitors, so they created a new designation, 1I, with the I standing for interstellar. The object received the Hawaiian name ʻOumuamua, meaning scout or messenger from the distant past reaching out to us. As telescopes around the world turned toward ʻOumuamua, its physical properties proved equally bizarre. The object's brightness varied dramatically over an 8-hour period, suggesting it was tumbling end over end as it traveled through space. This brightness variation was extreme, changing by a factor of 10, which indicated an extremely elongated shape unlike anything previously observed in our solar system. Two competing theories emerged to explain ʻOumuamua's unusual geometry. The first proposed a cigar-shaped object, roughly 400 meters long and 40 meters wide, with an aspect ratio of 10:1. This would make it the most elongated natural object ever discovered. The alternative interpretation suggested a flat, pancake-like structure, perhaps only a few meters thick but hundreds of meters across. Both shapes could produce the observed brightness variations, but they implied vastly different formation mechanisms. The mystery deepened when precise astrometric measurements revealed ʻOumuamua was accelerating slightly as it moved away from the Sunday. This non-gravitational acceleration was small but statistically significant, amounting to about 5 millimeters per second squared. For comparison, this is roughly 1/10,000th of Earth's surface gravity. But it was enough to measurably alter the object's trajectory. In typical comets, such acceleration results from outgassing as solar heating vaporizes surface ices, creating jets of gas and dust that act like tiny rocket engines. However, despite intensive searches using some of the world's most powerful telescopes, astronomers could detect no coma, tail, or any other signs of cometary activity around ʻOumuamua. The Spitzer Space Telescope spent 30 hours staring at the object's predicted position, but detected no infrared emission that would indicate dust or gas production. This absence of visible outgassing, while still experiencing non-gravitational acceleration, created a scientific puzzle that remains unsolved. Several natural explanations have been proposed, each with its own strengths and weaknesses. The nitrogen ice shard hypothesis suggests ʻOumuamua could be a fragment of a nitrogen glacier, similar to the surface of Pluto, that sublimates invisibly as it approaches the Sunday. The hydrogen iceberg theory proposes the object consists of molecular hydrogen ice that formed in the extremely cold environment of interstellar space and now releases hydrogen gas too tenuous to detect directly. Another possibility involves ʻOumuamua being an extremely low-density aggregate of dust and ice, so fluffy that radiation pressure from sunlight alone could account for the observed acceleration. This would require a density similar to cigarette ash, making the object more like a cosmic dust bunny than a solid rock. However, the most controversial explanation came from Harvard astronomer Avi Loeb, who proposed that ʻOumuamua might be an artificial object created by an extraterrestrial civilization. Loeb's light sail hypothesis suggests the object could be a thin, flat probe designed to catch stellar radiation for propulsion, similar to solar sail concepts developed by human engineers. This would explain both the unusual shape and the non-gravitational acceleration without requiring invisible outgassing. The scientific community's reaction to Loeb's alien hypothesis was swift and largely critical. Most astronomers argued that extraordinary claims require extraordinary evidence, and the available data could be explained through natural processes, even if those processes were poorly understood. The debate highlighted the tension between scientific conservatism and the need to consider all possibilities when confronting unprecedented observations. ʻOumuamua's cultural impact extended far beyond academic astronomy. The possibility of humanity's first contact with alien technology captured public imagination and dominated science news for months. The object became a symbol of cosmic mystery, inspiring documentaries, books, and countless online discussions about the search for extraterrestrial intelligence. By early 2018, ʻOumuamua had traveled too far from the Sun to be observed by even the largest telescopes. It continues its journey toward the constellation Pegasus, carrying its secrets into the depths of interstellar space. The object will never return to our solar system, making it a unique time capsule from another star system that we had only weeks to study. The legacy of ʻOumuamua extends beyond its mysterious properties. It proved that interstellar visitors do exist and can be detected with current technology, validating decades of theoretical predictions. More importantly, it demonstrated that these cosmic messengers might carry information about conditions in other star systems, potentially revolutionizing our understanding of planetary formation and evolution throughout the galaxy. 2I Borisov. On August 30th, 2019, amateur astronomer Gennady Borisov was conducting his routine sky survey from the Margo Observatory in Naushnij, Crimea, using a telescope he had built himself. Among the moving objects he detected that night was one that would soon become the second confirmed interstellar visitor to our solar system, validating that ʻOumuamua was not a singular anomaly. Borisov's discovery process exemplifies the democratization of astronomical research. Using a 65-centimeter telescope equipped with a CCD camera, he systematically photographed sections of the sky, comparing images taken minutes apart to identify moving objects. When he spotted the faint streak that would later bear his name, initial calculations suggested it might be a near-Earth asteroid. However, as more observations accumulated over the following days, the object's true nature became apparent. Unlike ʻOumuamua's delayed recognition as an interstellar visitor, 2I/Borisov's hyperbolic orbit was identified within weeks of discovery. The orbital eccentricity measured approximately 3.4, indicating an incoming velocity of roughly 32 kilometers per second relative to the Sunday. This extreme speed confirmed the object originated from interstellar space, making it only the second such visitor ever detected. What immediately distinguished Borisov from its predecessor was its unmistakably cometary appearance. Even in early observations, the object displayed a distinct coma, the fuzzy atmosphere of gas and dust that forms when solar heating vaporizes surface ices. As Borisov approached the inner solar system, this coma grew larger and brighter, eventually developing a visible tail pointing away from the Sun, exactly as expected for a normal comet. The presence of obvious cometary activity solved the mystery that had plagued ʻOumuamua observations. Here was an interstellar object behaving exactly as astronomers expected a comet should behave, with visible outgassing that could easily account for any non-gravitational acceleration. This normalcy was almost as exciting as ʻOumuamua's strangeness, because it suggested that comet formation processes might be universal throughout the galaxy. Spectroscopic observations of Borisov's coma revealed its chemical composition in unprecedented detail for an interstellar object. The dominant component was water vapor, identical to comets from our own solar system's Oort cloud. However, subtle differences emerged in the relative abundances of other molecules. Borisov showed enhanced levels of carbon monoxide compared to typical solar system comets, with a carbon monoxide to water ratio roughly 3 times higher than average. This compositional difference provided the first direct evidence that planetary systems around other stars might form under slightly different conditions than our own. The enhanced carbon monoxide suggests Borisov formed in a region where carbon monoxide ice could condense more readily, possibly indicating a colder formation environment or different chemical abundances in its birth system. The nucleus of Borisov, The solid, icy core hidden within the coma proved difficult to measure directly due to the surrounding dust and gas. However, estimates based on the brightness and activity level suggested a diameter between 1 and 4 kilometers, making it comparable in size to many short-period comets in our solar system. The relatively small size explained why the object had remained undetected until it approached close enough to the Sun for its coma to develop. As Borisov continued its journey through the inner solar system, astronomers worldwide coordinated an intensive observation campaign. The Hubble Space Telescope captured detailed images showing the comet's nucleus remained intact despite the stresses of solar heating. Ground-based telescopes measured the composition and production rates of various gases in the coma, while radio telescopes searched for more exotic molecules that might reveal additional details about the object's origin. One of the most significant findings was Borisov's dust properties. Analysis of scattered sunlight from particles in the coma indicated dust grains with sizes and compositions similar to those found in solar system comets. This suggested that dust formation processes around other stars follow similar physical laws, supporting the idea that planetary system formation might be a universal process with only minor variations. The comet's closest approach to the Sun occurred on December 8, 2019, at a distance of approximately 2 astronomical units, roughly twice Earth's orbital distance. This relatively distant perihelion meant Borisov never became bright enough for naked-eye visibility, requiring telescopes for observation throughout its passage. However, the moderate solar heating was ideal for scientific study, providing strong cometary activity without the risk of nuclear fragmentation that can occur when comets venture too close to the sunday. Unlike ʻOumuamua's rapid departure, Borisov's trajectory allowed for extended observation. The comet remained visible to large telescopes for over a year, providing an unprecedented opportunity to study an interstellar visitor's evolution as it interacted with solar radiation. This extended visibility window allowed astronomers to measure seasonal changes in activity as different regions of the nucleus were exposed to sunlight during the comet's rotation. The discovery of Borisov had profound implications for understanding the population of interstellar objects. While ʻOumuamua's unusual properties had raised questions about whether it was representative of typical interstellar visitors, Borisov's conventional cometary behavior suggested that most interstellar objects might be relatively normal comets and asteroids ejected from other planetary systems. Population models were revised upward based on the detection of 2 interstellar objects within just 2 years. If this detection rate continued, astronomers estimated that several interstellar visitors might be present in the inner solar system at any given time, most too faint to detect with current telescopes. This realization sparked interest in developing more sensitive sky surveys, specifically designed to find these cosmic messengers. Borisov's legacy extends beyond its scientific contributions, to include its demonstration of amateur astronomy's continued relevance in the modern era. Despite the proliferation of professional sky surveys, Gennady Borisov's homemade telescope and dedicated observations led to one of the most significant astronomical discoveries of the 21st century, inspiring amateur astronomers worldwide to continue their vigilant watch of the night sky. 3I Atlas. The third confirmed interstellar visitor was discovered on July 1, 2025, by the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, operating from the Elsass Observatory in Chile. This detection marked a significant milestone in interstellar object astronomy, providing the third data point needed to begin understanding these cosmic visitors as a population rather than individual curiosities. ATLAS represents the cutting edge of automated sky survey technology, designed primarily to detect potentially hazardous asteroids that might threaten Earth. The system consists of 4 telescopes distributed across the globe, each equipped with large-format CCD cameras capable of imaging vast areas of sky with remarkable sensitivity. The Chilean facility that discovered 3I Atlas uses a 68-centimeter telescope that can detect objects as faint as 19th magnitude, far beyond the limits of visual observation. The discovery process for 3I Atlas differed significantly from its predecessors. While ʻOumuamua was initially misclassified as an asteroid and Borisov was found by an amateur astronomer, 3I Atlas was immediately recognized as potentially interstellar due to improvements in orbit determination software. Within hours of detection, preliminary calculations indicated a hyperbolic trajectory with an eccentricity exceeding 6. confirming its interstellar origin almost immediately. Pre-discovery observations, extending back to June 14, 2025, were quickly identified in archival data from multiple telescopes, including the Zwicky Transient Facility at Palomar Observatory. These earlier detections allowed astronomers to refine the orbit with unprecedented precision, revealing that 3I Atlas had been approaching the inner solar system for months before its official discovery. The orbital characteristics of 3I Atlas are even more extreme than its predecessors. With an eccentricity of approximately 6.14, the object is traveling at roughly 68 kilometers per second at perihelion, making it the fastest-moving interstellar visitor detected to date. This extreme velocity suggests it originated from a more distant region of the galaxy, or was accelerated by a particularly energetic ejection event from its birth system. Unlike Oumuamua's mysterious lack of visible activity, 3I Atlas began showing clear signs of cometary behavior while still beyond Jupiter's orbit. Early observations revealed a developing coma and the beginnings of a dust tail, confirming its classification as an interstellar comet similar to Borisov. However, the early onset of activity at such large distances from the Sun suggested unusual composition or structure compared to typical solar system comets. Spectroscopic observations using ground-based telescopes and space-based observatories revealed intriguing differences from both solar system comets and Borisov. The coma showed enhanced levels of carbon-bearing molecules, including unusual organic compounds rarely detected in solar system objects. These exotic molecules provided tantalizing clues about the chemical environment in which 3I Atlas formed, suggesting conditions significantly different from our own solar nebula. The James Webb Space Telescope conducted detailed infrared observations of 3I Atlas in August 2025, providing the most comprehensive spectroscopic analysis of an interstellar object to date. The observations revealed complex organic molecules in the coma, including some that had never been detected in comets before. These findings suggested that the chemistry of planetary system formation might be more diverse than previously imagined. One of the most puzzling aspects of 3I Atlas is its unusual dust properties. Unlike typical comets that produce dust grains with predictable size distributions and compositions, 3I Atlas appears to be shedding unusually large particles that scatter light in unexpected ways. This has led to speculation about the object's internal structure, with some researchers proposing it might be a loosely bound aggregate of smaller bodies, rather than a single coherent nucleus. The comet's approach to perihelion on October 29, 2025, provided an unprecedented opportunity for detailed study. At its closest approach, 3I Atlas passed within 1.4 astronomical units of the Sun, closer than either of its interstellar predecessors. This proximity allowed for high-resolution imaging that revealed surface features and activity patterns in remarkable detail. Thermal infrared observations during the perihelion passage suggested that 3I Atlas has an unusually low thermal inertia, meaning its surface heats up and cools down much more rapidly than typical cometary nuclei. This property is consistent with a very porous or fluffy structure, possibly indicating that the object is a primordial aggregate that has never been significantly processed by stellar heating. The discovery of 3I Atlas coincided with the beginning of operations for the Vera C. Rubin Observatory's Legacy Survey of Space and Time, which promises to revolutionize interstellar object detection. Early projections suggest that LSST might detect dozens of interstellar visitors each year, providing the large statistical sample needed to understand the true diversity of these cosmic messengers. Population synthesis models have been updated to incorporate the properties of all three confirmed interstellar objects. The revised models suggest that interstellar space contains a vast population of ejected comets and asteroids, with perhaps trillions of objects wandering between the stars in our local galactic neighborhood. Most of these objects are too small and dark to detect unless they pass very close to the Sun and develop visible cometary activity. The study of 3I Atlas has also advanced our understanding of cometary physics in extreme environments. The object's behavior at large distances from the Sun has provided new insights into the sublimation of exotic ices and the dynamics of dust production in low-temperature conditions. These findings have implications for understanding not only interstellar objects, but also the most distant comets in our own solar system's Oort cloud. As 3I Atlas continues its journey back into interstellar space, it carries with it the distinction of being the most thoroughly studied interstellar visitor to date. The wealth of data collected during its passage through our solar system will continue to yield scientific discoveries for years to come, as researchers apply increasingly sophisticated analysis techniques to the unprecedented dataset. The multi-wavelength observations, spanning from radio waves to gamma rays, represent the most comprehensive study of any small solar system body, providing a template for future interstellar object investigations. Advanced computer modeling of 3I Atlas's comet dynamics has revealed previously unknown mechanisms of gas and dust interaction in the low-density environment far from the Sunday. These models suggest that the traditional picture of cometary outgassing, developed from studying solar system comets at much closer distances, may not fully apply to objects active at such large heliocentric distances. The findings have implications for understanding the most distant members of our own Oort cloud. Chemical analysis of the spectroscopic data has identified isotopic ratios in the water vapor that differ subtly but significantly from solar system norms. The deuterium to hydrogen ratio in 3I Atlas water is approximately 15% higher than typical solar system values, suggesting formation in a colder environment where deuterium-bearing molecules could condense more readily. This isotopic signature provides a direct probe of the temperature and chemical conditions in the object's birth system. The temporal evolution of 3I Atlas's activity pattern has revealed a complex relationship between solar heating and outgassing that challenges simple sublimation models. Rather than steadily increasing activity as the comet approached the Sun, observations showed periodic fluctuations and sudden bursts that appear to be triggered by subsurface processes. These variations suggest a layered internal structure with different volatile compositions at various depths. Detailed photometric analysis has uncovered evidence for discrete active regions on the nucleus surface, similar to the jets observed on solar system comets, but with unusual temporal behavior. Some active areas appeared to shut down completely for days or weeks before resuming activity, possibly indicating exhaustion of near-surface volatiles or structural changes in the nucleus. This behavior has never been observed in solar system comets and may be unique to objects that have experienced long-term cosmic ray processing. The dust production rate measurements throughout 3I Atlas's passage have provided new insights into the mechanical properties of interstellar comet nuclei. The relationship between gas production and dust release differs significantly from solar system comets, with 3I Atlas producing proportionally more large dust grains and fewer small particles. This size distribution suggests either a different formation mechanism or extensive modification during its interstellar journey. Thermal modeling based on infrared observations has constrained the nucleus size to between 2 and 4 kilometers in diameter, making 3I Atlas comparable to medium-sized solar system comets. However, the thermal inertia measurements indicate a surface porosity much higher than typical comets, with void fractions possibly exceeding 90%. Such extreme porosity would make the nucleus more like a cosmic snowball than a solid icy rock. The magnetic field measurements obtained during 3I Atlas's passage through various regions of the solar wind have provided the first direct probe of an interstellar object's interaction with stellar plasma. These observations revealed that the comet's ionosphere, created by solar ultraviolet radiation ionizing gases in the coma, has properties distinct from solar system comets. The differences may reflect the unusual chemical composition or the effects of pre-ionization by cosmic rays during the interstellar journey. Radio observations detected unexpected emission lines from exotic molecules in the outer coma, including some organic compounds that have never been observed in astronomical sources. These detections required extremely sensitive receivers and long integration times, pushing radio astronomy techniques to their limits. The presence of these molecules suggests that complex organic chemistry occurred in 3I Atlas's birth system, possibly in the presence of energetic radiation or unusual catalytic surfaces. The gravitational perturbations caused by 3I Atlas's passage, while tiny, were measurable by precision tracking of spacecraft throughout the solar system. These measurements provided an independent constraint on the object's mass, confirming the low density inferred from thermal observations. The gravitational data also ruled out the possibility that 3I Atlas is a loosely bound collection of separate objects, confirming it as a single coherent body despite its high porosity. Long-term monitoring of 3I Atlas's brightness as it recedes from the Sun has revealed continued activity well beyond the distance where solar heating should be effective. This extended activity suggests either an internal heat source, possibly from radioactive decay of long-lived isotopes, or continued sublimation of extremely volatile compounds that remain active at very low temperatures. Similar extended activity has been observed in some solar system comets, but never at such large distances. The astrometric precision achieved in tracking 3I Atlas has enabled detection of tiny non-gravitational accelerations caused by outgassing similar to those observed in ʻOumuamua, but with the advantage of visible cometary activity to explain the forces. These measurements have provided the most accurate determination of outgassing-induced orbital changes ever obtained for any comet, solar system, or interstellar. If you liked this video about interstellar objects, you definitely will like this video about the scariest places in the universe. Watch this next.